Assalamualaikum warahmatullahi wabarakatuh and good day. My name is Muhammad Afiq and I will explain about antenna and propagation assignment, which is about comparison, design and simulate an antenna. There are various different types of antennas used in telecommunication, but the patch antenna, sometimes known as a microstrip patch antenna, is the most prevalent. So for this assignment, I have chosen an article given, which is about design of reconfigurable dual band E-shaped microstrip patch antenna. So the article is about dual band microstrip patch antenna with E-shaped slot. A microstrip antenna, also referred to as a patch antenna, has a ground on one side of the dielectric substrate and the radiating patch on the others. This type of antenna possesses qualities such as ease of installation, low cost, lightweight, small size, and good performance. This assignment involves a true analysis of the design parameters, benefit provided, and technique utilized in creating the antenna in order to comprehend the performance differences between three similar types of antenna and build the antenna using CST Studio Suite Simulator. Problem statement: each and every antenna, even though they are similar in type, has slight difference in terms of performance and design approach. These differences need to be extracted and documented in order to understand the reasons. The antenna design need to be done based on an antenna from given article with 3 search journal articles using CST Studio Suite Simulator. Objective: to investigate the differences in terms of design approach and performance between the given article and our obtained related journal articles. To design an antenna that operate and emits similar radiation pattern profile given in our journal articles. Okay, this is our relevant article 1, the title Design of Dual Band Microstrip Antenna with U-shaped slot. Similar type of microstrip antenna with the article given to us. So the first properties is we were talking about VSWR. For the figure A, the first band is 2.4 GHz and figure B on the right side is 4.6 GHz band. So ideally VSWR must lie in range of 1 to 2. The VSWR ratio at 2.4 GHz, which is the figure at the left side, lies around 1.2964, and at 4.6 GHz, the VSWR lies around 1.2141, shown in this graph on the right side. When VSWR is near the 1, the better the antenna is. And for the next parameters, we will look at the geometry of the rectangular U slot, also the radial loss of both antenna, both band. So for the geometry is on the top side and the top side and the top view and the side of the U-shaped slot microstrip patch antenna. As you can see the dimension. Also, using the coaxial probe fitting method. And for the loss, the design antenna resonates at 2.4 GHz and 4.6 GHz respectively. The return loss for 2.4 GHz lies around negative 70.78 to 5 decibel, and the bandwidth is around 0.11 GHz. And return loss for 2.6 GHz, 4.6 GHz is around negative 20.2915 decibel, and the bandwidth is around 0.14 GHz. So if return loss, which is known for the microstrip antenna, is S11 parameters, is smaller than negative 10 dB, we will not see the impact from this reflection on the transmitter signal. So hence, the smaller the value, the better the antenna is. In the next parameter for relevant article 1, we will look at 2D radiation pattern for figure A, 2.4 GHz, and the figure B is 4.6 GHz. As you can see here, the red line is for 2.4 GHz. It radiates at phi equal to 0 degree. See the shape here is omnidirectional. Okay, one direction. And the purple line for the 2.4 GHz radiate at phi equal to 90 degree. So the main lobe here and the side lobe. And for figure B on the right side, for 4.6 GHz, sorry for the blurred image, you can see that the red line is for 4.6 GHz, radiate at phi equal to 0 degree. You can see that there are two main lobes here, like two main lobes. And radiate at 90 degree, which is the purple line. This the small shape here. You can see the pattern is quite unique. The main lobe, I think the main lobe is here, and this is the side lobe. It has three side lobe. And the next parameter, we will look at 3D antenna gain for A, which is 2.4 gigahertz, and B on the bottom side for 4.6 gigahertz. In microstrip patch antenna, the gain is between 5 to 8 decibel. From this simulated result, show the gain of the design dual band antenna shown in figure here. The A, which is for 2.4 gigahertz, is the gain is around 6.2 decibel, and for 4.6 gigahertz, figure below here, the gain is around 5.0438 decibel. So this is the shape, 3D shape, the figure. Okay. So for the second relevance article, the title is dual band printed T-shaped slot antenna with wireless local area network LAN application. So first, the parameter will look at the geometry of T-shaped patch antenna, also the return loss here. You can see in the top view and the side view, the shape slot consists of the horizontal component with parameter L1, L1 here, top side L1, W2, L1 and W2, W1, L1 and W1 also, the vertical component with parameter L2 and W2. The horizontal slot controls the resonate mode for 2.4 GHz band operation, while the vertical slot controls the resonate mode for 5.2 GHz band operation. So this is the dual band for 2.4 and 5.2 GHz for this second relevance article. And the bandwidth, as you can see here from this graph, two resonate mode at the desired operating frequency are successfully sighted. The low resonant mode has impedance bandwidth of 650 MHz with VSWR is less than 2, covering the frequency range from 2.19 to 2.84 GHz for the band 2.4. And the higher mode, measured impedance bandwidth is 640 MHz. It's also sufficient to satisfy the bandwidth requirement of the 5.2 GHz band. So 5.2 GHz band here, and the S1 parameter, which is around, I think around negative 24, and the return loss for 2.4 here is is lesser than negative 30. Okay. And the second parameters here shown the radiation pattern of two operating mode, 2D radiation pattern for 4.2 and on the left side and 5.3 GHz on the right side. Okay, this is the XZ plane. It's the side view, which is horizontal, and YZ plane is the top view, which is in vertical. In the side view here, from both figures show the radiation pattern at two operating mode of the test slot antenna are measured in a far field and a conic chamber, as shown in figure here. Both resonate modes are seen to be the same polarization planes and similar radiation characteristic. Yeah, for the dotted line is for 2.4 5 GHz, and the continuous line here is for 5.2 GHz band. Because as we can see, the shape here is almost similar to each other, but the size is slightly different. But the radiation pattern here, we can see there is two main loop. Okay, and the YZ plane, which is on the top view or the vertical side, you can see here the shape, the radiation pattern for both band almost similar shape. And the next parameter we will see the antenna gain for both band. You can see 2.4 GHz band and 5.2 GHz band on the right side. It is clearly seen that the measured gain are higher than 4.55 decibel and 5.2 decibel in 2.4 GHz and 5.2 GHz operation band respectively. So you can see the 2.45 here is more than 4.55 decibel, and the 5.2 is around 5.24 decibel. This is the measurement. And the third relevant article, which is titled Dual Band H Slot Microstrip Patch Antenna for Wireless Local Area Network Application. Also is the antenna with microstrip patch antenna with dual band H slot. Okay, the first parameter here, you can see the geometry of the H-shaped patch antenna. Okay, this is the parameter and units. The H-shaped slot here, you can see in the middle, and has the calculated parameters here. And the second parameter, we will see about the simulated antenna return loss and also the VSWR on the right side. For both band, you can see the figures here on the left side. The antenna has the maximum return loss of negative 40 at dB at 3.65 gigahertz and negative 20 dB at 5.76 gigahertz, which is two band resonance. Okay, which is a good antenna return loss, which is or good S11, which is less than 10 dB. And the VSWR shows the value is lesser than 2 for frequency range of 3.65 and 5.76 gigahertz both band. You can see here. Around 1 point plus something. The paper didn't really mention the specific value, but it stated that it's less than 2. Okay, the next parameter for this third article, we will see the 2D rotation pattern at figures A on the left side is for 3.65 gigahertz and B on the right side is 5.76 gigahertz. So the radio interpretation for red line is for the red line on the left side is for 3.56 gigahertz. Radiation pattern radiate at phi equal to 0 degree, and the purple line is radiate at phi equal to 90 degree. So this is the main lobe and the side lobe here. To the shape. And for the right side is radiate at 5.76 gigahertz. The red line for 0 degree, if phi equal to 0 degree, radiates at phi equal to 0 degree, and the purple radiates at phi equal to 90 degree. The shape are different, and the lobe has two main lobe, I think. Okay. Next parameter, we will see about the 3D dimension, the 3D radiation pattern. For the A is for 3.565 gigahertz and B for 5.76 gigahertz. See the radiation pattern. It gives the maximum gain of 8.09 dB and 9.09 dB at 3.65 and 5.76 gigahertz respectively. Okay, as stated in the article. Okay, this is the summary I've done for 3 related article to the article given from lecturer. So first is the design approach. The type of the antenna is the dual band microstrip patch. So the three articles is all dual band microstrip patch, but with different slot shape. Okay, the first is E-shape slot, which is given is the provided article from the lecturer and the author. First is the E-shape slot is the redesign from rectangular patch. The substrate mentioned is using FR4 loss-free with permittivity 4.7, simulated using CST Studio Suite, fabricate and measured using Vector Network Analyzer VNA, and also they are using SMA connector, coaxial radio frequency connectors. And the first relevant article from my finding is this dual band microstrip antenna with U-shaped slot, and this is the author. First is the U-shaped slot also using the redesign from rectangular patch. Okay, and the substrate used is 4.6, the permittivity substrate 4.6. Didn't specifically mention what type of substrate using, but 4.6 permittivity is within the range of FR4 substrate. The FR4 has the certain range, but the 4.6 is is within the FR4 range substrate. Maybe they are using FR4, and the simulation they are using the Unsoft HFSS version 30. So mostly they're designing the microstrip patch antenna using two two type of simulation, which is CST Studio and also Unsoft HFSS simulation. And the fabrication for usage slot, the article I found, the first article, relevant article, they didn't fabricate their antenna. They are only simulate antenna, and also the feeding technique. Also, they are using the coaxial feeding technique. And the below here is the design of the E-shaped slot antenna. And next, the design approach for the second relevance article that I found is T-shaped slot. This is the outer, and also they are redesigned from rectangular patch antenna with the substrate 3.5. Didn't mention specifically what type of substrate they are using. The substrate permittivity 3.5, which is from my research, it is possible using lossy poly mate because the permittivity is within that substrate range. And also the simulation using the electromagnetic simulator CST Microwave Studio. They didn't fabricate the antenna using. They are simulation. They are simulate only, and also using coaxial feeding technique, which is SMA connector, coaxial radio frequency connector. And the third related article that I find is a H-shaped slot, and with the author here, and also they are redesigned for rectangular patch. Uh, Actually, they are not particularly mentioned. They are using rectangular patch, but from the figure they are given, the dimension they stated in the paper, it seems like they are using rectangular patch antenna. They redesign rectangular patch antenna. So the substrate permittivity, they are using substrate telephone with permittivity 1.33, which is very low permittivity. And in simulation, they are using Nsoft HFS that also they didn't fabricate antenna, they only simulate, and also refeeding technique using coaxial with 50 ohm impedance. Okay. To summarize, mostly they are using the redesigned rectangular patch antenna in using the feeding technique of coaxial feeding technique. The substrate are vary according to the author preference and using the two type of simulation, which is ST and unsoft HFS. Also, the second properties we are measuring are the performance. Okay, the performance of three related journal with the article given to from the lecturer. Okay, the frequency for each shape is they are using 3.02 and 6.35 E38. There's level parameters for each shape slot. Negative 22 and 72, negative 30, 70.26 BSWR, around 1.70 and 1.32. Antenna gain 3.575 and 5.565, and bandwidth didn't stated for the each slot article that given from the lecturer. And the comparison in the frequency is very high. For this U-shape slot, they're using 2.4 and 4.6 frequency band. And the S11 parameters, they get negative 70 and negative 20 BSWR, around 1.2964 and 1.2141. Antenna gain with 6.2 and 5.0438 in the bandwidth. They mentioned that you get 0.11 GHz and 0.14. So from this comparison between the provided article and the related article that I found, I can assume that the the U-shape slot perform better compared to E-shape slot based on the 11 S11 parameters and the bandwidth. Also with the antenna gain. And the second related article here, frequency is very according to their author. The T-shape slot using 2.4 and 5.2, and the H-shape slot using, I think they are using specifically 3.65 and 5.72. Then the S11 parameter for the 2.4 is less than 30, and 5.2 is around negative 35. Didn't specifically mention, but it's within that range. The H-shape slot is around negative 40 and to negative 28 BSWR. For T-shape slot is they said they achieve less than equal to negative 2. Also, the H-shape slot stated the same. They didn't specifically mention the the specific value of the BSWR they get. Antenna gain for T-shape said that they get more than 4.55 and also more than 5.24 for 2.4 and 5.2 gigahertz band respectively. So 8 decibel and 9 decibel for antenna gain at H-shape slot for 3.65 GHz and 5.765 GHz respectively. And the bandwidth they get is 0.2584 GHz and 0.1212 GHz for T-shape slot, and the H-shape slot didn't state their bandwidth. So okay, so I can say that uh the U-shape slot still above the T-shape slot when comparison between the performance. So above the H-shape slot. So overall, the U-shape slot is performing better in overall performance based on the bandwidth as the S11 parameters in yeah, that two importance indicator. And for the antenna and antenna design and simulation, this is the design parameter value I'm using for the simulation that I will show next. Okay, this is the my design antenna design that need to operate an image similar radiation profile given in uh, my related relevance article. So this is the dual band microstrip patch antenna with dual slot. This is dual slot loading technique. Okay, from the article there is no this type of dual slot. So I think I will recreate or design a different type of dual slot, but that can emit the similar radiation profile based on the assignment requirement. Okay, this is design. First I will state that I'm using the material of copper inlay for the ground or the patch, and for substrate I'm using the FR4 lossy, and that's for the material. And the result has been compiled, and first we will look at the S11 parameter. Okay, this is the S11 parameter. Oh, first of all, my dual band is resonate at 2.4, 2. Okay, 2.4 and 5.2 gigahertz frequency band. Okay, and for S11 parameter, this is the S11 parameter that I get from the simulation result. You can see here the indicator one, so this is 2.4 gigahertz band. I get the S11 parameter around 20 negative 27.81766, which is less than 10 dB, and which is good. And but for the S11 parameter for 5.2 gigahertz, I didn't get the accurate measurement for 5.2 because the graph indicates that it gets around 4.9 gigahertz frequency band. So the readings, they get the accurate readings, but for the 5 gigahertz that I get here, I get around negative 14.793 decibel for S11 parameters. And for bandwidth, for 2.4 gigahertz bandwidth, for the calculation, I get 0.0268 gigahertz, which is very narrow bandwidth. Yes, I get very narrow bandwidth, which is very bad actually, because we want a wider bandwidth for better antenna, and I got narrow bandwidth. Maybe there is some mistake or in my calculation and in my parameters value that I need to change. And for this 5 gigahertz, I get the bandwidth around 0.0170 gigahertz, which is also very narrow bandwidth. which is not good for microstrip antenna, because microstrip antenna, the problem is narrow bandwidth, so we need to widen the bandwidth. But I think I get my calculation wrong here. In my parameter values, maybe I need to change to get the wider bandwidth. Okay, that's for LS 11 parameters. And next VSWR. Okay, from this graph and from this indicator one, around 2.4 gigahertz, I get around, wait, it's okay. I think I get around here. Okay, 2.42 gigahertz band, I get 1.08932 for VSWR, which is less than 2, and near to 1, which is very, very good with ASWR. And for 5 gigahertz, actually, I want to take 5.2, but the measurement I get only 5 gigahertz, which is not accurate measurement for 5 gigahertz band, 5.2 gigahertz band, but for 5 gigahertz, I get 1.4461 VSWR, which is also good, because it is less than 2. So VSWR overall is good VSWR. And next indicator, we will check the 2D and 3D result. I'll check the far field first. The far field. Check, we look at the 3D. Okay, so this is the far field, 3D far field for 2.4 gigahertz. You can see here, this is 3D design, which is omnidirectional. One directional from the shape, we know is bidirectional. Omnidirectional. One direction. And for the 1D, we can look here. Sorry, okay. The main loop and the side loop. The main loop here is omnidirectional, and the side loop. This is the 4.2 gigahertz far field view and 5.2 gigahertz. We check the 3D first. So this is the 3D radiation pattern. This radiation pattern actually very similar to U-shaped antenna, as I mentioned earlier. Let's see. Yes, this is the U-shaped radiation pattern, the 5.4.6 gigahertz, and this is my 5.2 gigahertz with here, almost similar. So in 1D, they are bidirectional. There are two main loops here. And for U-shape also, there's two main loops at the left and the right side, which is very, very similar. And for the 2.4 gigahertz, for the two 1D radiation pattern, also very almost similar design. The radiation pattern almost similar. Okay, and I think that's it for simulation demonstration. Okay, we can look at the E field for 2.4. Okay, this is the E field, which is radiated in the vertical, and the E field for 5.2, which is also radiated vertical, but this is the radiation animation. You can see here the difference between 2.4 and 5.2. And the H field for 2.4 radiate on the horizontal, you can see here, and 5.2 radiate in vertical. Okay, I think that's all for the simulation demonstration from me. Okay, I think that's all. So for the conclusion that I get overall from this assignment is that the design antenna, which is dual band microstrip patch with dual slot loading technique that I designed from the CST just now, emits similar radiation profile with U-shaped patch antenna, but didn't achieve good S11 parameters and bandwidth. The possible parameters and calculation error for my part. And the second is overall antenna design and performance from provided article and three relevant article obtained. The U-shaped Patch antenna perform better in terms of two important indicators, which are 11 parameters, return loss, and bandwidth. That's all from me. Thank you.